Anyway, doesn't matter. Nobody's probably waiting for us anyway. If you are waiting for us, guys, hello. All right now. Anyway, doesn't matter. Nobody's probably anyway. Come on. All right. So now I think we should be live if everything is the way, if it were the way it used to be. Now, is it now that they move things around, doesn't show whether it's live. Why doesn't it show me? I want to know for sure that I'm live.
At the top, it says YouTube at the top there somewhere.
Yeah, it said it's live on YouTube.
Where do you see that? Because I want to
Well,
know.
I saw it flash across the screen.
Yeah, but it needs.
Actually, if you click on the YouTube icon at the upper right,
I see it says live down here.
yeah.
If they just let me know where they're going to put, I mean, don't mess with me. Okay, I'm going to assume we're live now. And now I also want, come on, I had something else lined up here. All right. Okay, so we're getting started 7 minutes late. Hi, I'm Metta Spencer. Today we've got a good crowd of people who are experts on cloud cooling. And if you don't know anything about cloud cooling, you just stay with me and we're going to go on a trip to learn all about it. And today we have 5 people who are all experts in various, or at least they would like to be, some of them. Franz Weste for sure is an expert. He's in Germany. He's the developer and co-patent holder of the iron salt aerosol method of depleting carbon dioxide and methane. And he's got a new one that he's going to try out on us, although we've talked about it a couple of times before, but it's so new that we need to talk about it a lot more. So hello, Franz.
Hello, Metta.
In London is Clive Ellsworth, who his earlier claim to fame was being the co-founder of the Citizens Climate Lobby UK, but he's so involved with this iron salt aerosol thing that I think it's probably he's changing his identity to that.
That's right.
Is that fair enough?
That's fair. Yeah.
Okay, and in Ottawa, closer to home, is Robin Collins, whom I call on for everything when I need help. I wanted somebody to pitch in and give us a sort of a beginner's vision of questions about the kind of complicated technology that we're going to be discussing today. And Robin is a longtime friend and peace and environment activist in many of the organizations that I'm in. David Price is in someplace in British Columbia, where he says there's smoke that he can see from the forest fires from his house. He is a retired modeler of forestry for the National Natural Resources Canada. So he knows things about trees in particular. Oh, here comes Sander. Good for him. David Price, who I've just told you about, but here comes Sander Epima, whom I've not met before, but if I let him in, and if he gets his equipment functioning. Hello, Sander.
Good day. How are you?
Great.
Thank you.
Very good. Good to meet you.
Pleasure.
I was just about to introduce you, so I will say that the only thing I really know about you is that you're an investment consultant at See the Future, and
That's
that
correct.
must be a company that. Well, you tell me, is that a company that is trying to see how to make a good future, or are you just in to make a buck?
For sure. So it happens to be my acronym of my name. So there's a certain ring to it. If you want to look on the bright side, there's a lot of possibilities to create a better future together by working together on a better social paradigm and also involving nature and nature-based technology. So that's the essence.
You're exactly the kind of guy we all need. Somebody to make sure that we're doing good deeds with our money.
For sure.
All right, thank you. And these other folks I've just introduced, and you'll meet them there.
And we're live on YouTube, Sander.
Right.
Excellent. Thank you.
Okay, I think I'm going to turn to Clive first because the inspiration for this is we had a couple of conversations before. I think the last conversation that was relevant to this, I titled "Thanks to Chlorine," because I found out during that show that hydrochloric acid in clouds turns out to be an important new way of cooling the planet. And so it has something to do with chlorine, which is surprising. I wouldn't have thought we wanted chlorine in our clouds, but whatever. So that was just for me a beginning to look at this enlarged technological innovation that Clive and Franz are promoting. And I understand, I know very well that both of them been for a long time engaged in trying to promote a kind of technology that would remove methane from the atmosphere by using iron salts. And then they've been exploring other kinds of aerosols that might do different things. And I gather they're adding some new components to the game plan. So that's the interesting thing, is that we're expanding beyond just iron salt aerosol into other more ambitious projects. So Clive has written a 2-page clarification or help for the lay people because some of us don't even remember the acronyms for all these chemicals that we learned about in high school. And so we need Clive to help straighten us out. And would you do that? Would you sort of give us your clarification, Clive, and then we will try again to see if we can master this enlarged project of yours. Have I misstated anything so far?
No, everything you said is fine, and accurate. Yeah. Yeah. As you were speaking, and I've been thinking recently, it's important to emphasize that what we're proposing, what we're proposing is to mimic the way that nature already works, and the way that nature already works in the atmosphere. What the kinds of things we're talking about are very small amounts, very small proportion of the atmosphere. I mean, we know that the atmosphere is mainly oxygen, nitrogen, and so forth. Now it's got a bit more carbon dioxide, but there's aerosols. So there's tiny, tiny particles that are so small we don't see them. We don't know they're there, but it's bits of dust and all kinds of stuff. Pollen. Over the land you get pollen. You get actually there's a chemical called isoprene, lots of things, and
Even
this thing
bacteria, I understand.
in
Right?
bacteria, that's right, and this is what clouds, clouds form at a height where the air gets so cold that it can't hold its water anymore, and so it's basically dew forming, and dew forms on these aerosol particles and makes clouds. Um, and what it's not our discovery, but we've found very interesting scientific papers from several teams around the world who've pointed out that there's rather interesting chemistry, special, very useful chemistry that happens in cloud droplets, which is that they're called chemical radicals, they're called oxidative radicals. So atmospheric chemists are very familiar with the OH radicals, one oxygen, one hydrogen. It's very reactive, and it's in the air all the time, and it's just part of normal chemistry. It's not the whole atmosphere. It's a tiny, tiny part, but it's enough so that, for example, trace gases like methane, which is 2 parts per million, it's gone up to 2 parts per million. It used to be a third of that. It's up to 2 parts, but it's very powerful greenhouse gas. Methane gets removed by OH radicals. And so it's really very interesting for us to see that actually clouds appear to be, and we'd love to have the research funding to verify this. Well, some teams have already, they've shown it, but we want to, there's all kinds of things that we know that we can do that there's other chemistry. We mentioned HCl, hydrochloric acid. So, but tiny, tiny, tiny amounts that exist. For example, above coastlines, we know the chemistry that makes a little bit more HCl in the air above coastlines, which makes this reaction go faster, possibly 30 times as fast. So methane is getting removed. We think 30 times, let's say, as fast above around coastlines than it is over the ocean, because of the additional HCl that's in the air that interacts with the chemistry that's being kicked off, initiated by the smallest cloud droplets. So that's where we've.
Oh, wait a minute. Let me get clear about this. Coastline air is being.
Yeah. So right. So okay. So you might think, well, where does this HCl come from? Yeah. So yeah, I haven't explained it. The thing is, atmospheric chemistry is there's a lot going on in a small way, but it's complex, in these small amounts. So over coastlines, you have a bit more salt in the air from the sea salt wave, the waves crashing down on the beach. They produce salt spray, seawater spray. Some of it's so tiny that it doesn't fall back down into the ocean. It's the particles or the droplets from the wave surf are so small that they just get carried around in the air, and the air is turbulent. The air is warmer at this surface than it is up high, so there tends to be a lot of convection currents, what we call the boundary layer, the lowest layer of the atmosphere. And so and it's turbulent, so it carries these aerosol particles up. Now the thing is, there are also in the air, wherever you have vegetation, and especially where you have phytoplankton produce the smell of the sea. We all know if we go to the seaside, we know what it smells like. It has got a certain smell to it. So again, it's not most of it's just a tiny part of it. It's called dimethyl sulfide, what they produce. And again, it's complex, but it ends up producing acids, sulfuric acid. Sounds scary, but the amounts are, again, so tiny, but they become concentrated onto aerosol particles. If you can zoom right in on a tiny aerosol particle, you see it's actually very acidic. It doesn't matter if you breathe it in because it's so small, but it is very acidic. And that acid reacts with any sea salt, sodium chloride, so we have acid and sodium chloride, and the sulfate part of sulfuric acid displaces the chlorine. So we end up with instead of sulfuric acid and sodium chloride, we end up with after the chemical reaction, which is natural, it happens in the air naturally, is sodium sulfate and hydrogen chloride, which is HCl. That's a gas, and that moves around in the air. And when that gas, so does that make sense? That's where the HCl comes from.
Make sure everybody else thinks it makes sense, because that's the important thing. Yeah. David, did you put your question in? You unmute yourself, please.
I was simply saying, yes, I totally agree and understand.
Okay. I'll take this out then when I edit it. Go ahead, Clive.
The thumbs up.
Okay. Yeah, so hydrogen chloride is and I've learned all this from Franz, who's been doing chemistry all his life pretty much. Anyway, so HCl is a gas, but we've all heard of hydrochloric acid. It's the acid that makes our stomach acid. And HCl gas is, again, it's also attracted to water, to aerosol particles. If you have a salt particle, that's going to attract water. We know that salt kind of, it attracts water. It gets a bit damp. It's so in the air, these particles attract a little bit of water and enough to also attract the HCl gas. So they also become acidic. And then, again, we could write it all out. That so what then happens is so OH radicals. So if you want me to explain it, so an OH radical, when that interacts with hydrogen chloride. So you now get another reaction. The OH radical is very oxidative, and if you can imagine an OH and an HCl, the reaction ends up with water, H2O. We know that water is H2O. And what's get kicked out of that is a single chlorine atom. And that's also described as a radical because it's very reactive. Single chlorine atom on its own is kind of, you could say, looking for trouble. And methane molecules, that's a CH4, carbon with 4 hydrogens, is a rather inert molecule. It doesn't oxidize very easily. I mean, we know as soon as you burn it in the cooker, and that's natural gas, it burns very quickly, but that's a chain reaction. It suddenly gets hot and it keeps going. So, but at the temperature of the atmosphere, it doesn't oxidize very easily. It needs one of these radicals to really hit it and take off one of the hydrogen atoms. After that point, it then oxidizes and it's gone.
We're talking about oxidizing methane.
We're talking about oxidizing methane. That's right. And rather peculiar. It seems a bit peculiar, but the scientists, the atmospheric chemists are saying this, is that the chlorine radical oxidizes a methane molecule at least 32 times faster than the OH radical. Even though the OH radical is more oxidative, somehow or other, the chlorine radical does it more quickly. It's more likely. There's something about, I don't know what it is, the shape of it or something to do with the reaction. Maybe Franz might explain. But we know that it goes faster. Now, the thing is that when you've got that reaction, you end up with, the CH3, that's now unstable. That gets reacted. It goes away and becomes carbon dioxide. Still get carbon dioxide out of it, but carbon dioxide is much less of a warming gas than methane, much, much less. And you're back to having HCl because the chlorine radical has grabbed a hydrogen from the methane, from the CH4, and we're back to having HCl. So as long as there's a ready supply, an abundant supply of OH radicals coming from the cloud droplets, you only need a tiny bit of HCl, and that chlorine atom gets knocked out by the OH radical each time, oxidizes a methane, becomes HCl again, gets attracted back to a water molecule. So this is called catalysis. You've got a catalytic reaction. The chlorine atom is operating as a catalyst to rapidly remove methane.
Now, hold on. I've lost train of thought now. Is this all an explanation for why the coastal
Yes, it is. Yeah.
coast is the best place to do it?
Well, we're saying it's already happening. We think it must already be going faster at the coastlines because we know
Is it that you want to learn how to do it elsewhere too?
Well,
not just the coastlines, or why do we care? Why should I care that you're telling me this?
Well, because it has a rather important meaning. If we can measure the rate of methane removal in coastlines and find that it is indeed going faster, as it should be, because we know that there's more HCl in the air over coastlines because of this acid reaction I've told you about, and everything's fine. It's still a tiny amount. It means that if we're allowed, we can raise the level of HCl over vast areas of the ocean where, of course, there are clouds, and that will increase the rate of methane removal. It will the way we call it, enhancing the atmospheric oxidative sink, or the
but we're learning from the experience in the coastline how to do it on a bigger scale.
Yeah, it's telling us this is nature telling us this is how it works. Naturally on the coastline, if we can mimic that coastline behavior, it's still tiny amounts, but mimic that behavior. It's 1 part per billion is what Franz is saying. One part of HCl.
Now, hold on. Yeah. I want to make sure that I understand a little bit, because there are other people watching who don't.
Yeah. Okay. Yeah, we'll make it clear.
Yeah. But you've combined 2 different approaches. You've combined iron salt aerosol with
okay.
something else.
Iron salt, aerosol. So
And these two combinations, these two different ways of removing greenhouse gas are complementary and could be put together in a single package. And Sandra's going to go get some money to show how to do it. Is that our game plan?
let's see what Sander has to say about the second part of about finding the money. But iron salt aerosol. So Franz predicted 25 years ago that methane is getting removed from the air more where there's mineral dust right over the ocean because of a related reaction with iron 3 chloride or ferric chloride. So again, because of the chlorine atom, in fact, the iron.
I tell you what, don't even try to explain chemistry to me.
It's related.
I'll never get
so
it.
it's
But
related.
if I
It's
know
not the same thing.
what our project is, I know how to run a campaign. Now, if you
Yeah.
tell me what I'm supposed to go tell people to do, I will tell them.
Yeah. Okay. So it's the chemistry. So this is we've noticed. So Franz noticed one way that methane gets removed naturally over the ocean, and now he's noticed another way that methane is getting naturally moved over the ocean, and it doesn't involve putting iron 3 chloride in the air. We don't have to put any iron compound into the air. Well, actually, we still think it's still going to be beneficial to put much less iron, but still a little bit, because iron has other beneficial, that's other chemistry. Iron is very good at releasing the OH radicals from clouds. Again, atmospheric chemists know this. It's called the Fenton reaction. Iron is very good, again, in tiny, tiny, tiny amounts to have in clouds. So we still want to involve iron, but it's a different project, really. We're not now talking about just iron 3 chloride. We're talking about
Okay, are you saying
other
that
things.
you're giving up the whole project, iron salt aerosol, and replacing it with a different project?
We gave it up long ago. Other people, we've tried to persuade them. We've told them iron 3 chloride, there are much better ways of doing it. I don't know why they don't listen to us, but I think partly they say, look, we've got a project in progress now. We've committed a lot of effort into this. We want to see if we can get iron 3 chloride to work. And we've said, oh, okay, well, you keep doing that. We've got something much better. You don't need to put so much into the atmosphere. It's much closer to what was already happening in nature. If you mimic this part of what nature's doing. And so we're very glad that you're listening to us and you're giving us an audience.
Can I ask what the natural source of the chlorine is, the HCl, I guess, at the coastline is? What's the primary source of it?
So it's the salt, the chlorine in salt. You know that salt is NaCl, sodium chloride. The sodium chloride reacts with acids in the air, main acid being sulfuric acid, which it starts off as the smell of the sea, and it oxidizes in the air to become sulfuric acid. The sulfuric acid reacts with sodium chloride, and you end up with sodium sulfate and hydrogen chloride.
And the primary source of the H2SO4 is what?
So that begins as dimethyl sulfide. I'll keep it simple. Dimethyl sulfide, which comes from phytoplankton. It's actually something else, and it's all a bit complicated.
Okay.
But let's just keep it as it's dimethyl sulfide.
And so, are you suggesting another source than the phytoplankton that's human created to generate that?
Yeah. Yes. So HCl. So I've just given you one way that HCl gets into the air by natural means. There are a host of other ways that it gets into the air naturally. So we could just put tiny amount of HCl, into the air that spreads very widely. Simply chlorine. The concentration of chlorine in a swimming pool is way more than we would suggest in the ocean. You wouldn't be able to smell it. A tiny little bit of chlorine reacts with the water vapor in the air. That reacts with other gases. So there's another very important gas that comes from lightning and volcanoes. That also comes from combustion. And that's the NOx gas. So it's nitrogen oxides. These are photosensitive, so a bit like the iron 3 chloride, they're photosensitive. They produce OH radicals. There's a whole complex web of chemistry again to do with that. They help to form ozone in the air as well. We don't want too much ozone in the lower atmosphere, but it is involved with removing methane because again it produces OH. It's a hugely complex web. Atmospheric chemistry. I saw a lecture by a NASA guy talking about clouds, and somebody asked a question on atmospheric chemistry. He said, "I don't want to go there. It's like a black hole. Once you start talking about atmospheric chemistry, you never get out of it." And so I'm not even an atmospheric chemist.
Okay, that's the point. My point is, if we want to get people engaged with the project, we need to make it something that they can talk about within 2 minutes at the dinner table, and we've got to be able to give Sanders something that he can go and get people to invest in.
So let's say I think removing methane from the atmosphere is obviously vitally important if it can be done safely, and we really think it can be, because it's mimicking the natural process. However, even if methane, if you look at the physics of global warming, removing half the methane from the air would produce some cooling all around the world. Be excellent. Would take a lot of the pressure off. However, it would still not be enough. There's so much global warming, there's so much carbon dioxide in the atmosphere that something else is needed to provide sufficient cooling. And that is marine cloud brightening. So it's very fortunate that making clouds brighter, this is what Stephen Salter was talking about when he was with you, whenever it was a year ago. Unfortunately, he's no longer with us. When talking about marine cloud brightening, we began to say to Stephen, hey, do you realize that simply by making clouds brighter, they produce the better atmospheric chemistry that removes methane faster? So we're absolutely on your side. We don't want to compete with you. What you do will increase what we're suggesting here as well. So we are very much proponents of marine cloud brightening now, and we've been looking at ways to produce the aerosol particles small enough. So this is one of the problems, one of the sort of hurdles that many proponents, many people working on marine cloud brightening are trying to overcome, is making the particles, the aerosol particles, small enough. If your particles are too big, if you're not careful, you can make your clouds darker instead of brighter. You want to make them brighter. So that's another whole discussion.
Oh man, hold on. My understanding of marine cloud brightening is that it does not remove greenhouse gas. It simply reflects incoming radiation.
It does reflect. That's right, it does.
So
However,
why are you promoting it as a way of removing greenhouse gas?
Because these research groups around the world recently have been writing their papers, and we've been reading them. What they've been saying is that the very smallest cloud droplets produce OH radicals.
Clive, they found out that smallest droplets produce OH radicals, but not cloud droplets. They speak only from condensation droplets, and from you can make smallest droplets by ultra not noise. How do you call it?
Ultrasound.
Ultrasound.
Yeah. So not cloud droplets.
We found that we say, because we are since years trying to get smallest droplets from clouds. We say clouds can do the same. That hasn't been said by any other people. They only said it can be produced by condensation, by dew condensation, but not by clouds. We said it can be done by clouds.
What?
That's the first time we said it.
That
we
clouds can
produce
clouds produce OH radicals.
Yes. We say we are the first who said it, It
Right.
hasn't been in no other paper.
Right. But they've said that small water droplets produce OH radicals in
Yes,
these
but
papers.
not clouds.
Okay.
I only
it's-
wanted to say
Uh,
who was the first who said clouds make droplets.
oh, sorry. They
make
said,
OH.
okay. So they said water droplets, and
They
we're saying,
say-
well, clouds is made of water droplets, so it's the same thing in a cloud. Is that right?
Yes.
Okay.
Yes.
Yeah,
They
okay.
did say this because nobody knows how to make such small droplets we need for that.
Right.
So that means you can have these small droplets without clouds, is what you're
We
saying.
want to make droplets which are smaller than a micrometer in diameter.
Right. But
Yeah.
they can exist in the atmosphere absent clouds. They're just in circulation. Is that what you're saying?
I think Franz is saying in laboratories they're making them with ultrasound, so they're producing mists of water
Oh, I
using
see.
ultrasound.
And
Stimulating.
in the lab of Lyon
Yeah, Lyon in
University
France. Yeah.
in France, they found out that also condensation droplets do the same.
The condensation nuclei. Do you mean?
Yeah, droplets.
Yeah. So droplets
do the
made
same.
in clouds that condense onto aerosol particles.
No, not clouds. They say
Oh.
condensating droplets do it. That's the difference.
So they're not clouds.
No, they didn't say clouds. They say condense.
A condensing
droplets.
droplet.
Yeah.
Right. Yeah.
What's
But
the
that's what
difference-
happens in clouds.
What's the difference between a condensation droplet and a cloud droplet?
No, nothing. No difference. That's no difference. Yeah. But you must say, we want to do it with clouds. The others haven't had the idea to do it in clouds.
How would you?
They did it in lab.
How would you? Okay, so you can do it in a lab. So you can simulate clouds in a lab. Is that what you're saying? Or are you saying you can do this in the atmosphere absent
Right.
clouds? You don't
The
need clouds.
The last one.
Okay.
We think we can do it in the free atmosphere.
I'm sorry, but you just told me that cloud droplets and these condensation nuclei are the same thing.
But you can do them in clouds, but he's saying you don't have to do them in clouds. Is that right?
Also, clouds need also condensation nuclei to produce droplets.
Right.
Yeah. There's a lot of haze over the ocean. There's a lot of haze, in the morning, kind of mist, and it gradually clears. And so it's not like there's only cloud or something else. It's, there's a whole sort of continuum of phenomena.
Okay, you guys are going to have to help me. I'm not sure I can get any closer. David and Robin, you're not as ignorant as I am, but you're halfway there. So maybe you can help.
David,
I feel like I need a family counselor or something to help me understand each other, because I'm not getting much closer to understanding. And if I can't understand it, our audience can't probably either.
So I did have one comment, which is that in order to create cloud over ocean, you still need a significant moisture content in the atmosphere. But presumably, because you're looking at air that is over the ocean, you can pretty much guarantee that it will contain a significant amount of water vapor, so that when you add the cloud condensation nuclei, you will get cloud formation.
Yes.
That's
Yes.
right. This is where meteorologists come in, because they'll tell you that the air over the ocean, there are parts of the world where the air goes up and there's parts where it comes down. So as it goes up, as we know, it forms clouds because it gets cold and clouds form. And then they rain out, and then there's no water vapor left in the air anymore, and then it starts to come down, and you get parts of parts of the huge ocean where there's not many clouds because the air is mostly coming down in those places, and they're called the subtropical highs. And so we could put our, aerosol particles, with talking about making salt nanoparticles, in those places, and there's always a little bit of water vapor. It's never none at all. There's always a little bit. So you'll get a little bit of, it's called deliquescent, where it's the slightly wet salt, and then these HCl and they attract acid, and lots of wonderful, very important chemistry happens, especially photochemistry. So it's still worth having, even though it doesn't look like a cloud. You can't really see it. Maybe from a satellite you can see there's a bit of haze there. You can just about measure there's a difference. And actually, scientists who've done marine cloud brightening studies, there's one particular paper that's I think it's titled something like "As Effective as Clouds," something like. It's pointing out that actually haze, because haze lasts for days and days and days over the ocean, over that long period of time, it actually reflects away as much heat energy as clouds that only last a few days. Mm-hmm. So this haze in these dry areas, relatively dry areas, is still worth having. Sorry, Mette, I don't know if I've complicated it even further with that.
The difference is then that with the clouds you're going to get the reflection as well, whereas with this other, the haze, let's say, you may not get the reflection, but you get the methane neutralization.
You're getting
when I in the middle of the ocean, you have very small amounts of cloud condensation nuclei, between 20 and 50.
Yeah.
And therefore, the clouds in the middle of the ocean are are not so shiny. They are not bright. And the more condensation nuclei you provide to them, the more droplets they produce. But they produce the same amount of water in the same volume, not only with 2 droplets, for instance, with 1,000 droplets. That makes the clouds, the droplets are then much smaller because they hold the same water amount as the big 2 droplets of the normal ocean clouds. But if you give them much more cloud condensation nuclei, they produce white clouds with very tiny droplets. And these, the smaller the droplets are, the more OH radicals they produce. That's the interesting thing. And therefore, the white clouds, the brightened clouds, produce much more methane depletion.
Yeah.
They produce much more albedo cooling, and in the same way, much more methane depletion. That's a good thing. You get 2 strokes with one effect.
Okay, well, I'm going to try to lead some of this chemical stuff because I don't know how much of it we can absorb, but I'm going to assume that you got a package there that you want somebody to actually fund so that you can go do a pilot study or something. And that the question is, what does Sander have to tell people to get them to invest in your project? Is that the reasonable next step of the conversation as we move to an action that maybe our viewers may, if they understand you, may want to take? Sander, do you understand all this, and what are you going to do to try to get some money for these guys?
Sure, we've discussed this with friends and Clive with Blue Cooling, and think it's very important to assess what type of aerosols you're are working with in order to get some field tests up and running and to assess the environmental impact and do an actual impact assessment study that takes away some of the uncertainties that are currently in entering these public debates, if you will. So there's definitely a lot of interest. Also from the general public, there's ongoing debates and discussions, and people are actually interested to start investing in these type of climate solutions. So I think it's imperative to separate the discussion of marine cloud brightening and what type of elements would be best with the secondary objective of reduction of methane, which could be a nice combination. We should investigate all these types of potential aerosols that might be a good combination to create these condensate nucleids. So
Okay,
I'm excited.
Imagine I have a couple of $1 million loose around that I don't know what to do with, and you would like to get me to invest. Now, I have no idea why I should give you any money to put into this,
Sure.
because what would I get back? I mean, who am I? I don't see how anybody can make any money out of this, but please explain how this can be a business proposition for anybody.
Sure. So if you look at the increase of the albedo, the reflectivity of the clouds, the Earth, it's every decade we're losing 1% of albedo in its current state. So oceans are overheating. There are detrimental effects on our economy, on extreme weather events and whatnot. So for insurers, there's a clear business case to protect your premia, protect people against tornadoes in Texas, for instance, by reducing these bad weather events. That's just.
I mean, if I'm somebody in Texas, I appreciate it if you prevent a tornado or a hurricane, but I don't know how you're going to get me to pay you to do it.
Sure. Well, a lot of the debate goes on about carbon reduction and methane reduction. And methane, it's great if you're able to take it out of the atmosphere the way Frans describes and Clive. Really, there's been a large carbon shadow that's currently over the past centuries has been emitted in the atmosphere. So it takes a long time for that to actually go through the entire natural system or take it out. So in the meantime, it's important to also address global warming, the rising temperatures, and the effects it has on our current economy already. And in order to create business cases for this, you could consider cooling credits, biodiversity credits, those type of links to protecting biodiversity. As temperature rises, you see that there's an ocean acidification, and combining with pollution has destroyed and killed off the Great Barrier Reef. The Mediterranean Sea is also in a bad shape. We can improve the SML layer. We can increase the number of smaller salt particles that we're describing, as currently the level of aerosols are dropping and level of methane rises. So this is where you're getting a lot of bad weather effects, droughts in Spain, droughts in Italy, as well as in Greece. So there's actually a lot to gain. There's a lot to gain on the short term but these are.
You don't have to convince me that these bad climate effects are detrimental. What you got to convince me is that somebody's going to be able to make a profit from preventing it. So if I can invest in a company that's going to make a lot of money, then I would.
Sure. There's a lot of money being spent, and I'll allow you, David, if you allow me real briefly to just make a quick. Aside from these business cases will develop, it's very difficult if you're saying, hey, we're destroying the planet because we can't make a profit. Doing not so, that's actually absurd. So something is wrong in our system. of externalities, but that's a long story. If you look at the money that is currently flowing into all these defensive mechanisms for cities, coastal cities that are under heat stress, heat threats, crop failures, etc., you're not able to defend yourself against this continuously, right? You need to address the source and also the side effects. So addressing the source is reduction of carbon, which takes a long time. There's a lot of money pouring into this new industries to reduce carbon. If you only take a percentage of that, you would be able to implement blue cooling field tests at scale and cooling off the planet by cooling down at 4% of the ocean surface, cooling down the rest of the planet. So it's worth investigating. It's necessary if you look at it. You need to also address climate change, the temperature rise. So that's what I would like to say.
Okay, but somehow you were promoted to me as a guy who's going to get some money for these folks, and that sounds like you're ready to go out and make a pitch to some corporation or something that they should invest. And
Sure.
I don't know, still don't understand right now whether you're really in a position to do that. I could see how if you could get cities to say that they know that they've got to put in extra sewers or something, and that therefore to save the money of investing in sewers, they would rather invest in cloud brightening. So then maybe you could make some business deal right now.
If you look at
if
you look at taking out all the carbon that's required, if you want to cool and refreeze the Arctics, you need 70 times the annual energy budget of the US. It's undoable. So, but if you create little salt particles, you have an incredible leverage. It's very cheap to create this salt and to create this effect of these clouds. So, and you will reflect in thousands more of energy as what the energy costs us to create these clouds. So it's a mechanism that works. And Frans is obviously way more experienced to or Clive to explain the process.
The mechanism. I'm ready to accept that. I'm trying to find what kind of business interest would be ready to actually pay for the pilot study that you need to get going right now. I don't know.
David?
Well, it seems to me that the one industry that would be more than willing to support this is the insurance industry, because they could improve their bottom line simply by reducing their payouts. And I mean, we're talking about a global industry, which is going to have to be taking the hit on the consequences of extreme weather events, whether it's flooding or drought or fires, drought affecting agricultural production. Everything that we're talking about is ultimately a risk that can be insured and which is becoming more and more uninsurable. So the industry ought to be in there packing money into it. And by the way, governments should be doing the same, because ultimately governments become the default insurer in the event that the insurance companies can't cover the rest of the damage.
There's prisoner's dilemma in the fact that you don't in your own street, you don't pay for your own land for the lighting in the streets at night. Nobody is willing to pay, right? So it's a similar dilemma. It's a prisoner dilemma. These are governmental bodies that should step in to create the right type of governance, international agreements, and also enable an open source sharing of these type of technologies, not purely to make a profit, also to ensure that we if you look at there are crops failing now in India, in Germany. It's so global warming already has a severe impact on our food supply, and will have a severe effect also on water scarcity. So it's coming near a town near you.
So are you ready to go to an insurance company or to, say, a city municipal government and say, give me some money to pay for Frans's experiment? which he wants to do next year.
You can
For
see
instance.
you
Yeah.
can see how this does come down to the governance issue, because the entity that needs to put the money into this technology almost necessarily has to be a government or an international governance body, because who else is willing to cut costs that way? I mean, it's really about governments looking at ways to save money that would otherwise go into responding to the crisis. So this would be a preventative, cost-effective mechanism. So I can see the insurance side of it, but to me, it's governments are going to be putting the money up primarily, and you know they'll be setting up arrangements with companies, obviously. So there's a trickle down there, but governments are going to have to stand up, and it's going to have to be international to some extent. So you know, large entities, governments working together, agreeing that this is a lot cheaper to do this research than it is to you know, build 50-foot walls around the coastline to keep the floods from coming. You know, it's going to be a lot cheaper to do this.
David Price?
Well, just commenting, and I agree with Robin, but in a sense, we have this sort of global political phenomenon of populism and resentment of big government. And lots of politicians are going to get elected on the principle that they're going to cut taxes. People don't like paying taxes, but many of them are perfectly willing to pay for insurance. And so what can happen is that the insurance industry globally will have to put up its premiums, which is a way of getting the public to pay for the damage. But that is also going to be the source of revenue that could ultimately fund programs like this to reduce the risks. In the long run, the insurance company will be making money hand over fist because they're accumulating more money from their clients, but not having to pay out as much, presumably in the future.
Exactly.
I guess in time it will settle down, but that would be a business model, I would think, that the insurance companies could embrace.
And these damages are already accumulating year on year, and they will only become increasingly substantial. So if you delay this investment, you're making it more expensive.
Exactly.
If you're not doing it, yeah. What's the cost and the risk of not doing it? So there's a balance there.
Exactly.
Are you ready?
We have to pay somebody. The question is, who are we going to be paying? Right.
But also when? I mean, are you ready to actually go to an insurance company or a government and say, I want some money next month for this project? Or are you hoping that eventually public opinion will change enough so that the people will say, you know, tell their insurance company or their government that they want to have it done, and they will elect people who'll do it? See, that's the question. How quickly can you get action? I mean, you're an investment counselor, right? So that
it's definitely twofold. You need to strategize and talk to influencers, decision makers, and enable the proper information clearing for the general public to be involved. What happened with carbon? It's tremendous. Everybody's talking about saving the planet, reducing global warming if we stop emitting CO2 right now, but the effects will last on for centuries. So that there's an understanding that we need to act, and there's also a willingness. We just need to educate the people and investors to make them understand the relevance of solutions that are out there right now that we can start testing and evaluating and scale in order to scale them up, to also prevent immediate systemic collapse due to heat waves.
Suppose I do have a couple of $1 million that I don't know what to do with, and Franz comes to me and says, I want some of that, or maybe all of it. And in fact, I need a lot more than that to go do this experiment, which I can do next year if you give me the money now. How much do you need, Franz? And what would you do with it immediately? What would the next phone call would be to whom? Because you're going to have to set up an appointment to start getting a team together who can actually do this, the engineering and the logistics and stuff. Tell me what your next steps would be to actually do an experiment on the ground or in the air.
To bring together experts from the universities and discuss with them. Because if I, a small guy, will not have enough power to get this, but if we have convinced a group of experts and they go to the government or else, this could bring more, I think, than I personally do this. I need help. I need help for that.
Okay, well, there are organizations that do that. I was just looking at the Alfred P. Sloan Foundation, which funds meetings of mostly academics, apparently, who are interested in removing carbon from the atmosphere. I don't think they're funding things that are albedo related or based on reducing, increasing albedo, but I think they're on negative emissions is what they would like to call it.
If you want to negate the negative indirect side effects of all these CO2 emissions, so global warming, it's way cheaper to do it with albedo or reflectivity to increasing cloud coverage. So that's the business case. If you make polluters pay directly or indirectly, hold them responsible, they will be able to, you will be able to channel a carbon tax or of sorts or some other form of pollution in order for them to reduce pollution, and on the other hand to actually invest to address the negative side effects. So
okay, I'm willing to help promote a campaign as long as we know we have steps 1, 2, 3, and 4. We got to contract these people in order to get the money to do this, but are we going to work on albedo? Or are we going to work on carbon reduction? Let's have I think what we need is a real strategy so that the objective is to come up with a campaign with steps and whom shall I contact tomorrow kind of thing.
Sure.
Right?
Carbon reduction is important in the long run. In the short run, it's really increasing albedo reflectivity. If we don't do it now, in a decade, it may be too late. We have ocean surface temperatures rising. It's actually accelerating. This is very, very bad news. We should try and get to a sort of a new ecological stable state. And currently, tipping points are slowly tipping. So,
and additional. You speak from carbon in the air. Come later. Now, when we cool down, also phytoplankton become to grow and become to recreate, and this is a thing which sucks carbon from the air. If we do nothing, the ocean surface becomes much warmer, the stratification becomes more, and phytoplankton does not become the fertilization which is normally becoming from below, from the layers below it, because with rising warming, the stratification becomes more and more, and phytoplankton will go down more and more. That happens, and phytoplankton makes the clouds over the sea become lesser when the plankton becomes more restricted.
Thank you.
So
And
all
David?
is connected to each other.
This
That's
is also this is what Frans is saying is already happening in the Mediterranean Sea with heat waves as an effect, and that's something that we really need to prevent. So by investing in technologies, working out solutions that work in line with natural processes, so you can save the SML layer, the algae layer, that create more aerosols, and we can create more aerosols in the meantime to create more clouds. Those are solutions that really mimic nature and that are relatively affordable and the way to go.
David?
Well, I have two comments really. One is that I don't really, I guess I'm not sure on the status of how academia sees sort of radiation management, MCB, or any other technique. I mean, we've had this HPAC discussion, NOAC discussions, where I think there's a lot of consensus that there is a need to manipulate albedo, planetary albedo, because we are running out of time, and that other alternatives like removing CO2 or just in reducing emissions are not going to solve the problem fast enough. But I don't know where that academic consensus is, and it would be really, really important, and I think Frans mentioned this, to get that, build the consensus, if you like, within the academic community, because they can provide a lot of influence. But my other question is really to Clive and to Frans, which is, okay, so what is the minimal experimental design that you would come up with if you were sort of given the opportunity to spend not $2 million, but $200 million? It's got to be something in that kind of magnitude, but presumably there's sort of a minimal idea. I mean, how many square kilometers of ocean do you want to do an experimental treatment? Which areas of the ocean should be looking at? Should it be high latitude, mid latitude, tropical? So that you can at least sort of provide something to the potential investor on what exactly it is that you are talking about doing.
Can we talk about the project, Sander? Or
Sure. There's a project that we're assessing in Western Africa. So that's one of the with the Blue Cooling Initiative. That's one of the areas aside from the western parts of the Americas that might be useful to utilize marine cloud brightening to cool the rest of the planet. So that's what Frans is referring to. So go ahead, by all means.
Great. Clive?
Yeah, tropical areas. I was going to say, yeah, I mean, $200 million. We thing to understand is that Frans and I are a team working from home. Frans is retired, he's in his late 70s, and I volunteer part-time. I have to do other things to stay alive and pay the bills. So that's the kind of team we are. I've joined up with Frans because I think he has an incredible insight. You know, he never gives up. Look, he's still working. You can see all the files behind him. That's all his work. But it took Frans 15 years to find somebody to fund experiments, which was done in a German university. Then that person fell out with it's all a long story. It then took another 5 years for us to find someone to give $50,000 for Copenhagen University to get interested. These universities don't take an interest unless there's some money. And they look at us like, well, who are we? We're not even professors, we're not even academics. So, but Frans has come up with it, but now Copenhagen University have said, yeah, of course it works. Yeah, so they've come up with a huge roadmap for ferric chloride, for iron-3 chloride. It needs a bit more than us. It needs to be a bigger team than just me and Frans. And so for me to come up with and say, all right, here's a line item list of $200 million, I don't think, we can say with broad brush things like the tropical ocean, the atolls be great. We've recently come up with a way of doing it with actually sea salt. We do it with, people don't like the sound of ammonium chloride, even though it's a food additive. We could do it with it's possible to make sea salt nanoparticles the right size. I don't know. We think we can make them narrow enough size distribution, which is all these technical boxes have to be ticked. We think we can do that. So we focus on one problem at a time, solving the main problems. So the next thing to say, well, how would you spend 200 million? We need a bigger team to work out all those details.
I'm willing to help you guys. I just don't know how to do it until somebody gives me a list of email addresses and things to ask.
We're
Yeah.
working much like your HPAC coalition. We're working on similar coalition in Europe as well. So global coordination with the leading scientists, and there's interest from other groups as well to actually fund this research. So we have to move in time, before late is too late.
That's right. Can I say one more thing? I mean, another problem here is kind of ideology, and the academic institutions sometimes they discourage this kind of research because there's this ideology that if you find a way to allow clouds to safely cool the oceans, you'll be restoring ecosystems, preventing 150 species going extinct every day and all these things. But they say, no, you shouldn't be doing that because people will forget about reducing their carbon footprint. And so this is, am I using the right word here? Ideology. So Professor Stephen Salter, who sadly passed away earlier this year, I think it was this year, he was hounded out of his university. He was told he had to get out and take all his workshop with him for being a heretic, just to say, clouds can cool the oceans. And we learnt from him. We're carrying it forward without him now. And so academics are quite afraid to look at these, just look at something that can work, because they're afraid of losing their job or so this is part of the problem.
Clive, you're true. It's right. But if we focus on that and all we'll do is wring our hands.
Yeah.
There's no point in just wringing our hands. Let's say that if we can show people that we have a plan that can actually benefit them and we can show that it's likely to work, just keep hammering away at that and hope that it will have some impact. I think eventually, and already we're seeing cracks in that public opinion now is demanding people to do something practical. And so let's work on making sure we have a game plan that says here's exactly what we need to do by certain dates. Here's
great. There needs to be money. This is part, I think, what I'm trying to say. We applied for money for the first set of experiments.
Okay, and I don't even want to hear it.
Yeah.
I'm telling you, let's not talk about lamenting the fact that people are stupid. Let's agree that most people are stupid.
There needs to be money. There needs to be money. The academic institution.
We have to figure out exactly what we're asking people to do.
Oh, yeah.
And in a very practical sense, we want somebody with a strategy, and not only a strategy, but particulars, a checklist of things we have to do by certain dates in order to get this campaign going. You tell me that, and I'm going to do everything I can to help you.
Okay, I'll send you the documents.
Thank you. Time's up. We're about 7 minutes over time. So it's been fun. And I always think after I have one of these, we got to have another one, because we're sure not there yet, guys. We're really not there, honestly. But you're doing the right thing, but we just have to keep going. So bless your hearts, keep going, and I'll get back to you soon.